Assalamualaikum warahmatullahi wabarakatuh. So we meet again. Okay, so this is a lesson for quasi square wave inverter. So as you already know that we have already discussed about the square wave inverter, and based on the example that we have discussed, we can see that the THD output voltage of the square wave inverter can be quite large, maybe around 50% or 40% THD. So it is not quite good actually, but that can be actually reduced if we put a filter circuit, which is the low pass filter circuit at the output terminal of the square wave inverter. Okay, so it will significantly reduce the THD to up to maybe down to 5%. Okay, so that is actually the square wave inverter is the simplest inverter to actually convert DC into an AC voltage. Okay, and this is quasi square wave inverter. So still the topology or the circuit is actually still we are concentrating on the full bridge inverter. Okay, actually the difference between quasi square wave and square wave is actually how we control the signal of these four switches. Okay, for quasi square wave the output voltage is quite different. Okay, so meaning that for one period, okay, this is half period. So actually the output voltage of the quasi square wave will be this one. Okay, and if you recall back for the square wave, the angle is actually the voltage waveform is this one. So this is your VDC, this is negative VDC, and this is also the same VDC and negative VDC. Okay, so this is quasi square wave and this is actually a square wave. Okay, so if we compare this two output voltage of the full bridge inverter here using a quasi square wave and square wave, actually if the voltage, if the waveform is more resemble to a sinusoidal, so the THD will be actually lower. So if we compare this waveform, quasi square wave and square wave, we can definitely say that the quasi square wave is much resemble to a sinusoidal. So meaning that this quasi square wave THD is much lower than the square wave. Okay, this is actually because based on the analysis that has been done, actually we have what we call this actually a firing angle or triggering angle here. Okay, this is actually in quasi square wave, what we can do is actually we can eliminate one harmonics component. Okay, so because of that, we can have the THD much lower than the square wave. So for example, if we have a square wave voltage versus frequency, so we have this V1 and we have this spectrum V3, V5 and V7. Okay, by using quasi square wave, we can eliminate these harmonics V3, V5, V7, V9 and so on, but only one harmonics will be eliminated. And logically, okay, so the harmonics that we want to eliminate should be harmonics number 3, right? Because this third harmonic is the highest harmonics values, and also it is actually the what you call the location is the nearest to the fundamental. Okay, so it is benefit if we can eliminate these third harmonics, because when we eliminate these third harmonics, definitely the THD will be lower, and at the same time, as you can see here, the cut-off frequency when we applying low-pass filter can be made much larger compared to if we didn't eliminate the third harmonics. So right now, instead of when we have this third harmonic here, so our frequency cutoff may be here, but when we eliminate the third harmonic here, we can actually widen the low pass filter frequency cutoff more than the frequency, the original frequency cutoff, without eliminating the third harmonics. So there are two advantages. The first one, we can eliminate the harmonics by, so meaning that the THD is lower, and the second one is actually low pass filter design is much easier. Okay. Okay, so maybe you will ask me how to choose the which harmonic that will be eliminated. So actually we can select which harmonics that we want to eliminate by using this formula. Okay, so for example, actually it is related to the angle that we use. So the angle will determine what harmonics that we will actually eliminate. Okay, you are using this formula. This is 90 degrees, and this is the harmonics number that you want to eliminate. So if you want to eliminate the harmonics number 3, so the alpha should be 90 over 3. So the alpha that you need to use should be 30 degrees. So meaning that this is must be 30 degrees. Okay. If you want to eliminate harmonic number 5, so meaning that your alpha should be 90 over 5, should be around this one is 18 degrees. Okay. But however, there are also there are several disadvantages of using this quasi square wave. The obvious disadvantages of using this quasi square wave is that the fundamental value, which is your V1, is decreased. Okay, if for the square wave, your V1 magnitude should be 4 VDC over pi. But for quasi square wave, the voltage V1 will be reduced because of the angle that you are used. Okay, and this value of V1 depends also on the angle that we are using to eliminate the harmonics. Okay, so for quasi square wave, the generic expression for the voltage is can be written as a Vn is equal to 4 VDC over n pi cos n alpha. Okay, so if you want to eliminate harmonics number 3, where your alpha is 30 degrees, so your V1 has a value of 4 BDC over pi cos n is equal to 1, is actually alpha is 30 degrees. Okay, and for V3, So 4 VDC over 3 pi cos n is 3 multiply with 30 degrees. So this should be 0. So that's why when we select 30 degrees, okay, your harmonics number 3 will be eliminated. Okay, and so on also for V5. So harmonic number 5 is 4 VDC over 5 pi cos 5 multiplied with 30 degrees. So there will be some value. So meaning that our concern is on the fundamental, because when we use Quasi square wave, we can see that the output voltage of this waveform will be reduced. Okay, so that's all for the Quasi square wave inverter. So we will continue on the most advanced switching techniques, that what we call the pulse width modulation.